Right. In this video, we're going to briefly review some of the four main function families that you've already been introduced to in algebra: linears, quadratics, powers, and exponentials, with a really quick emphasis on power and exponential functions. Right? You've spent a lot of time dealing with linears and quadratics in algebra. You've got the general equation, right, often called slope-intercept form, because it tells you the slope of the line and the y-intercept. A lot of the times we will, from here on out, kind of use this ax plus b, getting out of the m for slope, just to keep it consistent with the lettering that we use for everything else, where we just say, hey, a and b are constants that talk about the shape of this function. For linears and quadratics, oftentimes we use the transformed form, right? For linears, we call it the point slope form, where it takes that parent function, like y equals x, and transforms it, shifts it up by some y1 units, and shifts it right to the right x1 units, and dilates it vertically by a factor of m in this case, right? Called point slope form because it has the point x1, y1, and the slope m in that case, but we also say it's transformed form. For quadratics, right, your general equation here, ax squared bxc, again, a, b, and c just give you some of the characteristics of that graph. Right? A tells you how wide it is and if it's concave up or concave down, opened up or opened down. Right? C tells you where the y-intercept is. Right? In the transformed form, you'll have a question like that in your homework this afternoon. Right? It takes that parent function, y equals x squared. Hopefully that's right. Good review from Algebra 2, and transforms it. Right? Shifts it to the right h units, up k units, and dilates it again by a factor of a. What I want to spend most of the time here talking about is the power functions and exponential functions, right? Power functions and exponential functions are two functions you're familiar with, but they're so similar that people tend to trip them up. And I just want to emphasize here, like, what are some of the characteristics of them that you could see, right? If I saw a graph of this, I would know it was a power function, or I would know it was an exponential function. If I saw the equation, I would know what it looks like. Right, so power functions, general equation, y equals a times x to the b power. We're not going to deal with any transformed forms of power functions or exponential functions. We're always going to have them just kind of centered at the origin, right? At 0, 0. We're not going to be shifting them left, right, up, down at all. Right? So power functions can take three different shapes depending on the b value, basically. The a value also tells you some things. The a value, if it's positive, it's going to be open up like all of these. If it's negative, it's open down. None of the examples that we will be seeing right now will have negative a values. Everything that we're going to be dealing with is going to be like going up. But the b value tells you a lot about the shape of this thing, right? If the b value is positive, greater than, nope, this should say greater than a 1. If the b value is greater than 1, right, it is going to be an increasing and concave up graph. Like, it's an increasing and increasing at more and more rapid rates. But a key feature is that it goes through the origin there, right? Because exponential functions also have some functions that are increasing and concave up. But a keynote feature of the power functions is that it goes through the origin here. Right? If the b value is less than 1, but still positive, right? That's what this, right? Greater than 0 means it's positive. Less than 1 here, it's still an increasing power function, still goes through the origin here. But now instead of being curved upwards, it's curved downwards. It's increasing at a decreasing rate. Every time I move further to the right, it increases by a little bit less than it did before. And then when you switch into the negatives, when you go less than 0, it completely inverts, right? And is this decreasing concave up function that has asymptotes here. It never actually crosses the y-axis at all, and asymptote on the x-axis there. So I put in this little Desmos piece here with the sliders, and you can see, right, power functions often are just in that first quadrant here, right? Again, if a is positive, it's up in quadrant 1. As soon as you go negative, it dips down. We're going to be dealing mostly with things up here. We don't deal with that second quadrant because, or like the second and third quadrants, because you can see, right, depending on the sign, or like the, how big this is, when you go negative here, it can be positive, it can be negative. It kind of does this dance where sometimes it doesn't exist at all, sometimes it's positive, sometimes it's negative. Right? So we only deal with first quadrant graphs for almost the whole time that we're looking at this. Right? If b is a large number, when I zoom in here, right, it's that concave up, right? Increasing at an increasing rate. As soon as I get b at 1, then it's just a linear function, right? Like, doesn't matter. Now I'm just y equals a times x to the 1 is just x. So it's just this linear function that happens to go through the origin. When I get less than 1, again, back here we get some weird things going on. It might not exist at all, and it might be below, it might be above. But when I'm less than 1, between 0 and 1, it's this increasing still, but concave down, right? If it's 1/2, right, x to the 1/2, that's the square root function, right? These fractional or decimal values here make this become like the square root of x. X to the 1/2 power is the square root of x. Right? And then if I keep going at b equals 0, again, pretty boring. It's just a flat line wherever the a value is, right? A is 4.1 there. But when I get less than 0, right, now I start to get this, again, interesting shape here. Right? Doesn't matter, it can be greater than 1, less than 1, negative 1. You get the same shape no matter what. And I get asymptotes along both axes here. Right? So again, we tend to just ignore the 0 and the 1 because they're boring, barely even power functions. They're just straight lines. But everything in between there has its own different characteristics. Right? For exponentials, it's very similar, right? This equation, power function, it's a times x is the variable to the power of b, this constant. A and b are constants in here. X is my variable. For exponentials, very similar looking, but the b and the x have just switched places. It's a times some constant to this variable power. Right? I can't just multiply a and b together, right? Orders of exponents or orders of operations, I always do the exponents before the multiplication. So it's not just like some number to the x power, it's some constant times a different constant to this exponent. I do that operation first and then multiply by a. Okay? But the graphs, if b is greater than 1, again, same kind of deal as here. If b is greater than 1, I get this increasing concave up graph. The main difference between these two is that this always will have some non-zero y-intercept. Okay, this one up here will go through the origin every time, unless we added on like plus something here, but we're not ever going to do that for right now. Right? But this exponential function will always have some non-zero y-intercept, again, as long as I'm not adding or subtracting anything here, which we won't. Right? And it has this asymptote at the x-axis. Right? This one has no asymptote, it actually hits that spot. So very similar with similar conditions, that b value being greater than 1, but the graphs look a little bit different. You're going to have to be able to tell those apart. Right? When it's between 0 and 1, right, this thing switches. Right? Instead of going increasing, it starts to be a decreasing exponential function. Right? This would be exponential growth. This would be exponential decay here. Right? So again, this is very similar, not to the same like b condition here. That's a very different graph, but it's very similar to this where it's decreasing and concave up. Right? They look pretty similar. The main difference is the power function has an asymptote at the y-axis, and the exponential function will still have some non-zero y-intercept. It's going to cross that y-axis at some point. Exponentials exist in quadrants 1 and 2. Right? Still asymptote at the x-axis, just like this one does, right? So the only difference here is that that has a y-intercept, and this one has an asymptote at the y-axis. And if b is less than 0, if b is negative, then it just goes haywire, right? Negative numbers raised to different powers, right? They kind of alternate between negative and positive. So if I have like negative 2 squared, that's positive 4. If I have negative 2 cubed, that goes down to negative 8. So we get this weird thing. And if I have, right, negative 2 to the 2.7th power, like what does that even mean? So we only ever deal with positive b values, no negative b values here at all. Yeah, so if I can scroll over, it's going to let me. There. Right. You can see my a value just tells me where the y-intercept is, right? No matter what I have here, that's my y-intercept. Negative just goes below. We will, again, be just dealing with things up positive here. Right? So if it's greater than 1, I get this exponential growth, right? As soon as it dips into the fractions, and again, when it's at 1, boring, right? Just a flat line at y equals a, because 1 to any power is just 1. Right? But as soon as I go less than 1, I get this decreasing function that looks very similar to this up here. Again, that one just has an asymptote. The power function has an asymptote. The exponential function will cross that graph somewhere guaranteed. Right? Again, dip less than 0, and it just dies. Right? You can find some points. If you do this on Desmos itself, like if you go to the website and try to type this in and go negative values, it might show you like a bunch of dots kind of going above and below the axis there, but we're not going to deal with that. So again, right, really focus on differentiating these two things. A times x to the b, when the constant is in the exponent, it's a power function. When the constant is up there, it's a power function. When the x value is in the exponent, it's an exponential function. Right? And yeah, power functions will always either go through 0 or be dividing by 0 to make this asymptote every single time, right? It's never going to have a non-zero y-intercept. Exponential functions will always have some non-zero y-intercept. So I hope that helps with the practice problems.